Welcome to the 35th lecture in the open course on diffusion in multi-component solids. In this lecture, the concept of correlated jumps is introduced. It is shown that the diffusivity as defined by Einstein's equation needs to be modified by a correlation factor for diffusion of substitutional atoms guided by defects. A general expression is also derived for substitutional diffusion via vacancy mechanism in any cubic lattice. So, last couple of classes we went over the theory of random walk. Now, we would like to apply it to derive expressions for diffusivity in crystalline solids, specifically in cubic lattices. So, just a recap over last couple of lectures, we derived the expression for diffusivity in terms of mean square displacement as d equal to average of x square over 2 tau, where x square inside triangular bracket denotes the average of square of x projections of net displacements of all the atoms, and tau is the small time interval. If we consider the mean square displacement, which is denoted as average r square, it can be given as average of x square plus average of y square plus average of z square. X, y, z here denote the projections on x, y and z axis of the net displacement vector r. In isotropic diffusion, the distribution is spreading equally in all directions. So, obviously, we have average of x square equal to average of y square equal to average of z square, and so we can write average of r square, that is the mean square displacement, as 3 times average of x square. So, if we substitute in this equation, we get mean square displacement over 6 tau as the diffusivity. We also derived the expression for mean square displacement, that is average of r square, which we can write as average of r square is n lambda square times 1 plus 2 over n double summation of average of cos theta I j, and the first summation I goes from 1 to n minus 1, and second summation j goes over I plus 1 to n. Now, this expression for mean square displacement is valid for any type of jumps, whether random or not. If the jumps are truly random, then we have seen the average of cos theta I j here is 0, and so we get the expression as average r square equal to n lambda square. Now, if we consider the small time interval tau, and if gamma is the successful jump frequency of atoms, then in time interval tau the total number of jumps n will be gamma times tau, and so if we substitute back in d, we get d is equal to gamma tau lambda square over 6 tau, or d is equal to 1/6 gamma lambda square. So, this is the equation that we had already derived using the simple atomic jump model a few classes back. Now, in order to evaluate the successful jump frequency, we need to consider two contributions. For any successful jump of an atom, two conditions have to be satisfied. First, the atom has to gain an energy equal or greater than the activation energy for migration, and second, the next site or one of the nearest neighbor site has to be vacant so that the atom can jump onto that site. When these two conditions are satisfied, a particular vibration will convert into a successful jump. So, we can write gamma as nu0 exponential minus delta g m by r t times x1v. Nu0 here is the Debye frequency, that is the number of times an average atom vibrates per unit time. The second term, the exponential term, basically represents the probability that a particular vibration will have an energy equal to or greater than the activation energy for migration, that is delta g m, and x1v represents the probability that a particular site is vacant. X1v is basically the equilibrium concentration of vacancies. So, we are assuming all the vacancies are randomly distributed in the crystal. We can write x1v as exponential delta S1v vibrational by R times exponential minus delta H1v by RT. So, if we substitute for x1v and then substitute for gamma in D, we get the expression for D as D equal to 1/6 nu0 lambda square, and if we combine the entropic and enthalpic terms together, then we write exponential delta Sm plus delta S1v vibrational divided by R times exponential minus delta Hm plus delta H1v over RT. Here delta Hm is the activation enthalpy of migration, delta H1v is the enthalpy of mono vacancy formation, delta Sm is the entropy of migration, that is the difference in the entropy of equilibrium state and the state of saddle configuration, and delta S1v vibrational is the vibrational entropy change associated with a mono vacancy formation. Now, if you see the first term including nu0 lambda and the entropic term, they are relatively independent of temperature. The second exponential term is strongly dependent on temperature. So, usually the temperature independent terms are combined together and denoted as D0. So, we get the expression for D as D equal to D0 exponential, and delta Hm plus delta H1v is denoted as Qd, the activation energy for diffusion over RT, and thus we get an Arrhenius type of equation or the Arrhenius type of temperature dependence for the diffusivity term, which is obvious because diffusion is a thermally activated process. Now, this expression is valid for diffusion of an atom by vacancy mechanism. But if we consider the diffusion of a vacancy itself, remember when an atom jumps into a vacancy, the vacancy is making a reverse jump. So, we can also consider diffusion of a vacancy. When we are considering the vacancy diffusion itself, since the vacancy concentration is typically very low, less than 10 to power minus 4 at most temperatures, for any given vacancy all 12 nearest neighbors in FCC for example should be occupied by atoms. The probability of finding a vacancy next to a vacancy is very, very low, and so at any given instance the vacancy can jump onto any of the nearest neighbor site, and so the diffusion of a vacancy truly represents random walk. So, when we consider the diffusion of a vacancy, we do not need to consider this term x1v. because the probability that the next site is vacant is 1 almost at all times. And so, the only contribution to the activation energy for diffusion of a vacancy will be from the activation barrier for migration. And so, for a vacancy, we can write d vacancy is equal to 1/6 nu 0 lambda square exponential delta Sm over r times exponential minus delta Hm by RT. Similarly, for an interstitial diffusion, the jumps of an interstitial will represent true random walk, because even in case of interstitial, the equilibrium concentration of interstitials is typically very low, and so the probability that there would be an interstitial in the nearest neighbor interstitial site of an existing interstitial will be very low. And so, at any instance, the interstitial will have all of its nearest neighbor site available for jumping. And so, the interstitial diffusion also represents true random walk, and even in case of interstitial diffusion, the only contribution to the activation energy for diffusion will be from the activation barrier for migration of the interstitial. Obviously, the migration barrier for interstitial will be different from that for a substitutional diffusion. So, we can write the similar expression as vacancy for interstitial diffusion 2, which would be 1/6 nu 0 lambda square exponential delta Sm by r times exponential minus delta Hm by RT, and to denote interstitial we will put superscript I over delta Sm and delta Hm. Now, coming back to the expression for diffusion of an atom by vacancy mechanism, this expression needs a little bit of correction, because we assumed that the atom is making a random walk while deriving this expression, and it comes from the expression for average of r square, that is the mean square displacement, which was n lambda square. This was true only when we are considering random walk. When the jumps are not random, then we need to use this more general expression here, that is we cannot take cos theta ij, the average of it, as 0. Let us see how. So, if we consider for example the 1-1-1 plane in an FCC lattice, suppose we are considering the diffusion of this atom X. So, the first time a vacancy arrives at any of the nearest neighbor of this atom X, it is a random process. So, a vacancy will randomly arrive on any of the nearest neighbor of X, and the atom X will make a random jump into that site. So, let us say the first random jump was from X to this site V here. So, after the jump, the vacancy is in the middle here and the atom is at X. Now, the second jump of X would no more be random, because now there exists more than random probability that the vacancy exists as a nearest neighbor of X, because the X had just exchanged with this vacancy. And what would be that probability? Of course, it will not be unity, but it will be more than random. Why is it not unity? Because vacancy itself is making random jumps, and for vacancy there is no barrier for vacancy formation as for the diffusion of X. The only barrier for diffusion is the migration barrier, and so the number of successful jumps of a vacancy per unit time will be much higher than that for the atom X. So, the vacancy itself will make n number of jumps, and after making n number of jumps, it can come back to one of the nearest neighbor site of x, and then this x will make its second jump into that same vacancy. Then that jump will no more be random, because x is exchanging with the same vacancy. The extreme case would be, after the first jump, the x will immediately jump back onto the same vacancy. So, it will be a reverse jump, and this reverse jump will nullify the contribution to the diffusion from the previous jump. And so, we need to apply certain factor to this expression for D, which will take into account this correlation effect, and it is done by applying a factor f in the expression for D. So, f is called the correlation factor, because the next jump of the atom x is no more random, it depends upon the previous jump, and these are called correlated jumps. Now, the same vacancy can exchange with atom x multiple times, and such a sequence of jumps of an atom into the same vacancy again and again is called correlation chain or a correlation sequence. If a fresh vacancy arrives on nearest neighbor shell of x, and then x exchanges with that fresh vacancy, the first correlation sequence is broken, and the new correlation sequence will start with the new vacancy. And it is important to determine this correlation effect. This correlation factor accounts for this correlation effect. If we define the correlation factor, it is defined as mean square displacement when the jumps are correlated divided by mean square displacement assuming completely random jumps. If we look into this expression for r square again, when the jumps are completely random, the average of r square is only n lambda square, and in a sense this summation of average of cos theta I j gives the contribution from the correlated jumps. So, f is essentially 1 plus 2 over n sigma average of cos theta I j I equal to 1 to n minus 1 and j equal to I plus 1 to n. So, we need to determine the average of cos theta I j, and I and j vary from 1 to n minus 1 and I plus 1 to n. So, we need to consider the combination of each jump with every other jump that occurred after it in order to evaluate the correlation factor f. Now, let us try to determine this correlation factor here. So, if we expand the summation inside, we can write f is equal to 1 plus 2 over n summation I goes from 1 to n minus 1 would be cos theta I plus 1 plus cos theta I plus 2 plus cos theta I plus 3 and so on. Now, fortunately, we do not need to consider the pair of each jump with another jump that occurred after it, because for any cubic lattice we can show cos theta I plus j is equal to average of cos theta I plus 1 to the power j. So, we can illustrate this for the case of simple cubic. So, let us consider the simple cubic lattice unit cell here. Suppose the atom x has made its ith jump from A to x here. So, ith jump of x is from A to x, and so the atom is now at position x and the vacancy is on A. The x has 6 nearest neighbor sites, which are denoted as A, B, C, D, E, F here. Now, on its I plus first jump, the atom x can either jump back to A, for which cos theta I plus 1 would be minus 1 because it is a reverse jump, or it can jump straight into B, which would be a forward jump onto side B, and the cos theta I plus 1 for that would be plus 1, or it can jump into one of these 4 sides C, D, E and F, for all of which cos theta I plus 1 would be 0, because these jump vectors would make an angle of 90 degree with the first jump vector A x bar. So, if we find the average of cos theta I plus 1 here, the average of cos theta I plus 1 would be the number of atoms Na that make this reverse jump to A times cos theta I plus 1 corresponding to that jump, which is minus 1, plus number of atoms that make jump onto side B times the cos theta corresponding to that jump would be plus 1. We do not need to consider other 4 jumps, because the cos theta for those would be 0 divided by the total number of atoms. Now, if you look at n A over n total is the fraction of atoms which have made the reverse jump back to A. So, it can be considered as the probability that an atom makes a reverse jump. Let us denote it as PR. So, this becomes minus PR. Similarly, NB by N total is the probability that an atom makes a forward jump. Let us denote it by PF plus PF. So, we get average of cos theta I plus 1 should be equal to PF minus PR. Now, let us consider the combination of ith and I plus second jump. For that, we need to consider all the sequences I plus 1 and I plus 2, because I plus 2 jump will depend upon I plus first as well as ith jump. So, let us consider this table here. Let us denote the jump of x from left to right by a right arrow and from right to left by a left arrow. Now, a left arrow may indicate a reverse jump or a forward jump depending upon the previous jump, because these are correlated jumps. So, the ith jump of atom x here was from A to x, and so let us denote the ith jump as left arrow. Now, I plus first jump may be a reverse jump or a forward jump. So, if I plus first jump was from right to left, it would be a forward jump, the probability of which would be PF, and if it was from left to right, it would be a reverse jump, the probability of which would be PR. Now, there will be 4 possibilities for I plus second jump depending upon what was the I plus first jump. The I plus second jump might be again from right to left, the probability of which would be PF, because it is a forward jump with respect to the I plus first jump, the first possible I plus first jump, or it can be from left to right, the probability of which would be PR. For the other possibility of I plus first jump, the I plus second jump again would be, if it was from left to right, the probability would be PR, because it is a reverse jump with respect to the previous jump, and if it is from left to right, the probability would be PF. So, if we write the probabilities for the first sequence, it will be PF times PF will be PF square. For the second sequence would be PF times PR. The third sequence would be PR square. Fourth sequence would be PR times PF. And if we see the combinations of ith and I plus second jump, for the first combination the two jumps are in the same direction. So, cos theta I plus 2 would be plus 1. For second, the two jumps are in the opposite direction. So, cos theta is minus 1. For the third one again, the two jumps are in the same direction. So, the cos theta would be plus 1, and for last one it will be again minus 1. So, the average of cos theta I plus 2 would be PF square minus 2 PF PR plus PR square. If we sum this and multiply by the corresponding cos theta I plus 2, we get this, which should be equal to PF minus PR square. So, we can show cos theta I plus 2 should be equal to average of cos theta I plus 1 square. We can keep doing this for I plus third, I plus fourth jump, and we can show that cos theta I plus j should be equal to cos theta I plus 1 to the power j, and this we can show for any cubic lattice. So, we have shown cos theta I plus j is equal to cos theta I plus 1 to the power j for any cubic lattice. This is important, because when I have to consider cos theta I plus j, I have to consider combination of every jump with every other jump that occurred after it. But if I have to consider only cos theta I plus 1, I have to consider only successive jumps of the atom. And when number of jumps n tends to infinity, is cos theta I plus 1, that is the average of cosine between the successive jumps will be independent of I, and that is why this result is important. So, let us substitute this back and to the expression for f here, and let us try to derive the expression for f. So, f is equal to 1 plus 2 over n summation of cos theta I plus 1 plus average of cos theta I plus 1 square plus average of cos theta I plus 1 cube, and so on. If we take average of cos theta I plus 1 common, get 1 plus 2 over n average of cos theta I plus 1 summation of 1 plus cos theta I plus 1 plus average of cos theta I plus 1 square, and so on. I varies from 1 to n minus 1. Now, this series can be approximated to 1 over 1 minus average of cos theta I plus 1. So, we can write f is equal to 1 plus 2 by n cos theta I plus 1 summation of 1 over 1 minus average of cos theta I plus 1. The I goes from 1 to n minus 1. Now, as I said earlier, as n tends to infinity, or for large values of n, the average of cos theta I plus 1 would be independent of I. That means, it should not matter which pair of successive jumps we are considering, the average of cosine between the two successive jumps will be same for any pair, the average taken over all the atoms. So, the expression will boil down to, if I substitute for average of cos theta I plus 1 as C, it will be 1 plus 2 over n times C, and since this will be same for all values of I and I varies from 1 to n minus 1, we should be factor of n minus 1 times 1 over 1 minus C. Since n is large, n minus 1 by n is approximately 1, and so we get the expression for f as 1 plus C over 1 minus C. So, we derived the expression for correlation factor f, and this is valid for any cubic lattice and for diffusion of an atom by vacancy mechanism. So, the correlation factor depends upon two factors: the geometry, which is given by the crystal structure here, and the mechanism of diffusion. In this case, this is for diffusion of atom by vacancy mechanism. So, for example, in cubic lattice, if the diffusion is occurring by interstitial C mechanism, in which the atom diffuses by forming its self interstitials, then the expression for correlation factor will be different. Similarly, the correlation factor for vacancy mechanism in a tetragonal lattice would be different. So, next couple of classes we will look into the specific expression for f in different cubic lattices, FCC, VCC, diamond cubic, etc., and we will consider specifically the vacancy mechanism of diffusion. Now, it should be noted that the average of cos theta I plus 1 will always be less than 0 for the cubic lattice, and so f will always be less than 1. This is because, as illustrated here, considering the jumps in 1 plane of an atom x, the second jump of atom x here will most probably be back into the same vacancy. So, that is the most possible sequence, and this nullifies the contribution to diffusion from the previous jump, and since this reverse jump is most possible, it kind of indicates that C has to be less than 0. The average of cos theta I plus 1 has to be less than 0. So, we will stop here for today. Thank you.